The strategy dynamics of collective systems. Strategic decisions in the context of engineering systems have a long-term and irreversible impact on the system's architecture. This work builds on previous research that seeks to understand the structural forces that influence these strategic decisions in systems of systems, where the actors responsible for each of the constituent systems are managerially or operationally independent of each other. We have identified strategy dynamics, a framework from game theory, as a useful device to approach this question. I will begin this presentation by introducing you to the current understanding of strategy dynamics in the literature. Next, I will present a motivating example of an engineering system where we can apply this paradigm. Then I will discuss some of the scaling challenges of the framework. As we advance, I will discuss our proposed approach to tackle such challenges. I will then go back to our motivating example to show you how we can apply our proposed approach, and finally, I will conclude this presentation by discussing opportunities for extending this work. What we currently know as strategy dynamics in the literature refers to the presumed rational strategic stability of individual and collective behavior in 2x2 games. A game is an abstract representation of a strategic decision-making setting involving multiple players, each with a finite number of individual strategies available. And 2x2 means 2 actors with 2 strategies each. We can represent a 2x2 game using a bimatrix. The rows list the strategies of actor 1 and the columns are the strategies of actor 2. We refer to the first of their strategies as a status quo or a starting point, here in dark blue, and their second option is called the alternative, here in yellow. Each intersection of rows and columns shows you the expected value of each actor in each of the possible collective strategy outcomes. In our work, we are interested in the differences in value when switching from one strategy to another. In particular, the loss of deviating from the status quo towards the alternative strategy. Each actor has one deviation loss for every possible strategy the other actors play. For example, actor 1's deviation loss is P1 minus S1 when actor 2 plays the status quo strategy, and T1 minus R1 when actor 2 plays the alternative. Similarly, actor 2's deviation loss is either P2 minus S2 or T2 minus R2 when actor 1 plays the status quo or the alternative strategy, respectively. We assess these deviation losses because we know from the literature that they are critical to understanding the strategic stability of these 2x2 games. These deviation losses are called structural fear and structural greed, FNG for short, and the combinations of positive and negative values of these structural factors characterize 4 primary strategy dynamical domains. These are the quadrants on a rectangular coordinate system with fear along the vertical axis and greed along the horizontal axis. Counterclockwise, starting from the top right, we have defection, then we have biostability, harmony, and finally coexistence. These labels barely make sense without giving meaning to each of the strategies. To do that, let's consider an example of a system of systems where each of the 2 actors must choose between opening their system so the other can take advantage of it, or keeping their system closed and limiting integrability. Here, the latter strategy is status quo, and the former is the alternative. In this context, harmony dynamics on the lower left would promote full integrability. Defection dynamics on the top right will favor disjointedness between the systems. Biostability, the top left, would favor a unanimous course of action, either fully integrated or fully independent systems. And coexistence, bottom right, would lead to anti-coordination, that is, one system will remain closed while the other will open. So how is this relevant to engineering systems? Well, what if we are trying to understand what these structural forces imply for the integrability of an urban transit ecosystem? Take, for instance, the NJ Transit Corporation, and let's assume there is a growing push for integrating these systems and achieving synergy. Let's focus on NJ Transit's passenger management system. The performance of this system is affected by external systems outside NJ Transit's control, namely traffic management, safety and communications, and many others. As with urban transit in New Jersey, the actors responsible for these systems are managerially and operationally independent. Now, we represent the trade-offs to improve the integrability of this urban transit ecosystem as a volunteer's dilemma. The volunteer's dilemma is a game model that helps us illustrate the tension between competing individual and collective benefits. On one hand, an individual status quo strategy is to keep their system closed. In the context of the volunteer's dilemma, this means not volunteering, our dark blue strategy, which we also label using the Greek letter phi. On the other hand, the alternative strategy is to open the system. This is our volunteering strategy, which we color yellow and we also label with the Greek letter psi. If you are an actor in a volunteer's dilemma, 3 rules determine your expected value. Rule 1. Your expected value always stays the same when you volunteer, regardless of what others do. We can represent this with the value 0. When others volunteer, you can increase your value by not doing so. That is, your expected value is positive. An example of this is using open tech to develop your product, but not contributing back to the open technology communities. Finally, Rule 3 says everybody will face harsh consequences if no one volunteers. We can represent this as a negative payoff. This outcome could result from focusing too much on achieving individual technological advantage while overlooking mutual interdependencies with other systems. Back to our urban transit ecosystem example. Let's consider 2 actors. Actor 1, overseen by NJ Transit, provides passenger management solutions. And Actor 2, overseen by the New Jersey Department of Transportation, designs and maintains the traffic management system. Moving from a status quo to an alternative strategy will have an irreversible impact on the ecosystem. And when we look at the possible strategic outcomes, we can have a better understanding of the incentives that could work in favor or against the actors embracing of synergistic system integrability. Given 3 possible levels of expected value, again, positive, null, or negative, we expect to observe positive outcomes favoring only closed systems who take advantage of others who have opened their system. For a single actor, such an outcome would be more attractive than committing to mutual integrability. But if everyone lets this structural greed dominate their decisions, they could face a major setback. In biometrics form, we now see this is coherent with a low level of fear and a high level of greed, which are linked with consistence dynamics, the one domain that favors anti-coordination. So far, we have considered a scenario with only 2 actors, but most real-world settings involve many more actors and complex connections between them. These are the scaling challenges that the framework faces. To illustrate this, let's go back to our game in its normal form and let's count the number of possible outcomes with respect to the number of actors. which in the 2x2 case is 4 outcomes. With 3 actors, we have now 8 outcomes. With 4 actors, we have 16 outcomes. And for any number of actors in general, we have 2 to the n outcomes that would result in 2 to the n minus 1 deviation losses per actor. And at this point, it is not clear how we can classify the emergent strategy dynamics. So this is what our proposed approach attempts to solve. It can be summarized into 2 steps. Let's illustrate them using a 3x2 volunteers dilemma. First, we dissect the game observed by each actor, in this case actor 1, into several smaller 2x2 games by grouping the other players into those who would play together as one and those whose strategies are presumed to be fixed, with the assumption that strategic actions are irreversible and they would only transition from the status quo, dark blue Greek letter phi strategy, to the alternative yellow Greek letter psi strategy. This leads to 5 possible player-reduced games. In one instance, actor 3 always plays the status quo. In another, actor 3 always plays the alternative. Similarly, there is a game where actor 2 is the one that would always play phi, and there is another game where actor 2 is the one that would always play psi. Lastly, there is a game where both actors 2 and 3 align their strategies. The next step is to distribute actor 1's deviation losses across these 5 possible player-reduced games, and we classify each of these smaller games using the earlier strategy dynamics framework. In this example of a symmetric 3x2 volunteers dilemma, we observe that 3 of the 5 player-reduced games exhibit coexistence dynamics, and the remaining 2 exhibit defection dynamics. And we take this result to our fear and greed rectangular coordinate system, and we call this set of points the actor's strategic hindrance space. There is a nice formula that allows us to calculate the size of a strategic hindrance space as a function of the number of actors n, and there are shortcuts we can take to understand how the deviation losses are distributed. Going back to the volunteers dilemma, we learned that coexistence are the only dynamics that emerge in the 2x2 case. We just learned that with 3 actors, coexistence emerges in 60% of the games, and defection emerges in the remaining 40%. And if we increase the number of actors, we observe that the defection dynamics take over. As we discussed earlier in this presentation, such dynamics are associated with disjointedness, and they would disfavor integrability. This could also be considered as an alternative explanation to the emergence of the bystander effect in social settings, which reinforces the usefulness of the volunteers dilemma in explaining settings where individual and collective objectives may be in conflict. Extending this approach to our motivating example, let's consider the actor responsible for safety and communications in the New Jersey urban transit ecosystem. In this case, this is the NJ Transit Police, the only transit police agency in the United States with a statewide authority and jurisdiction. They are also, for the most part, managerially and operationally independent. So let us represent these relationships between these 3 actors using a complete directed graph. On the right, we have the strategic hindrance spaces of each of the 3 actors. And one interesting property of the volunteers dilemma is that it has as many pure equilibrium points as actors. In this context, an equilibrium refers to a strategic outcome from which no economically rational player would deviate. In this setting, every time that one and only one actor volunteers. We wonder what would happen if the graph was not complete. What if we want to remove this edge representing the incidence of actor 3 on actor 1? Let's do that, and I want you to pay attention to what happens to actor 1's strategic hindrance space. Did you see it? Without that edge, a portion of the defection dynamics observed by actor 1 have turned into harmony dynamics, which we know would favor increased system integrability. We also see that the number of pure equilibria has decreased by 1. Let's add 2 more actors and a bunch of additional links. Now, not only do network interventions have the potential to facilitate the emergence of more favorable strategy dynamics, we also see the possibility of impacting the number of pure equilibria. And as we rearrange the network, we can have a better understanding of how to manage potential strategic outcomes for different network topologies, as well as different incentives. We see many potential avenues moving forward. We believe our approach can prove useful in advancing strategic engineering design research, and we look forward to collaborating with many other researchers in this realm and adjacent areas to understand the emergence of strategy dynamics on the different collective incentives, impact of network topologies on mitigating unfavorable dynamics, considerations in the study of evolving networks, development of larger strategic decision-making experiments, that is, with more than 2 actors, studying the emergence of these dynamics in real-world settings, applications in incentive mechanism design for engineering systems, applications in adjacent areas like biological systems, and many more. This work has been supported in part by the US National Science Foundation. If you are interested in this and other work on collective systems and design, or if you have any questions, please don't hesitate to visit our linked web pages. We'd be more than happy to chat with you. Thank you so much for your attention and have a nice day.